Section 1.2, we're going to take a look at right triangle trigonometry. Some of this is going to bleed back into geometry. I mean, some of this already has in section 1.1 anyway, but triangles are commonly used in trigonometry and in geometry, so there's kind of an overlapping piece of this. We will move to things that are specifically trigonometry pretty soon, but forming a basis of this is a good plan. So some starting pieces. So right triangles are triangles that have one right angle. The hypotenuse is the side that's opposite the right angle. And then the legs are the other two sides. The Pythagorean theorem is one that's probably very familiar to you. It's a squared plus b squared equals c squared. And on the diagram, a and b are on these sides. Or you could switch those two, that's fine. And C is the hypotenuse over here, with that being your right angle. So when the triangle is a right triangle, this allows us to take any two sides and find the third side. So we'll do one real quick where we're finding the third side of a triangle. This is the triangle that we're starting with. So we've got a side length of 2, and we've got a hypotenuse of square root 5. This is my right angle. And we're looking for the missing side. You can call it whatever you wish. I'm just going to call it A. And then with the Pythagorean theorem, we would set this up then that the unknown side is A squared. The other leg is the 2, so it's 2 squared. And then the hypotenuse is square root of 5, and we would square that. So with each of those pieces, 2 squared is 4, square root of 5 squared gives us just 5. And if we subtract, a squared is 1, and a would then be 1 as well. Typically speaking, if you've been in an algebra course recently, you might remember that when we put square roots on things, we put pluses or minuses, right? And in some sense, we're going to see some of that happening here, but for an actual triangle, it's measuring a length, and lengths are positive, so we don't have to worry about that when a triangle is given. If we're looking at a coordinate in space, which we will be at some point, you are going to see some of those positives and negatives coming back into play. So don't think they went away for good. Another hangover from geometry is SOHCAHTOA. Nod your head if that sounds like something you've heard before. Okay, so this is a relationship between sides of the triangle and an angle of the triangle. So you have to identify an angle for this to make sense. The angle that's mentioned down here in all of these trig functions is the angle theta. And SOHCAHTOA tells us about sine, cosine, and tangent. So in particular, the SO is that the sine is the opposite over the hypotenuse. That's where those letters are coming from, which is what you see written down here. Right? That's what the S for sine is, the SO, O for opposite, and H for hypotenuse. Ca is cosine. So the cosine is the adjacent over the hypotenuse. And then TOA is tangent. And then the tangent is the opposite over the adjacent. Now, the triangle, maybe I should have drawn that in to start with, and I didn't, but that's okay. We'll get it in there now. The triangle itself would look something like this. We're going to have a right angle. SOHCAHTOA is for right triangles only. It doesn't work for all triangles. And we would have some angle, so this would be theta. So if the theta is the one here at the bottom corner instead of the top corner, because we could put it in either location, we could be referencing either angle. The hypotenuse is always the side opposite the right angle. That's clear. That's always the case. But the theta itself tells us which of the other sides are the opposite versus the adjacent. So opposite is the opposite angle of theta. So in this triangle, this would be the opposite. It has to be across the triangle from it. And the adjacent is the side that's actually touching or forming part of that angle. So the theta is being formed by the hypotenuse angle and the adjacent angle, and then it's opposite of what we're calling the opposite angle. And you'll see we have these same 3 trig functions showing up down here, sine, cosine, tangent. And then these down here are reciprocals. So the sine and the cosecant go together. So the way I always remember it is that each of them has a co that they go with. right? So we have sine and cosecant, but then it's cosine and secant, right? Two cos do not go together. So they form these pairs. And then we have our tangent and cotangent, and that's the one that's easy to remember because it says its own name when it says the co part of it, right? And they're just reciprocal. So this one's opposite to hypotenuse. So the cosecant is hypotenuse over opposite. And as we go, you see the same thing for secant. It's hypotenuse over adjacent. And then cotangent is adjacent over opposite. All of this has to reference an angle. If it doesn't have an angle, it doesn't mean anything. It's like throwing out a square root and saying, square root equals 7. Well, no, that doesn't make any sense. Square root's a function. It does something, right? A secant, a tangent, a cosecant, a cotangent, a sine, a cosine, they all mean that we're going to do something to whatever's inside of it, just like the square root does something to what's under it, okay? So we're going to look at a specific triangle and do the same sort of thing. We're going to find those 6 trig functions. And you will see that the angle theta has to be referenced in the picture or it doesn't make any sense, and we do have that. And this is the same picture that we saw before. I wanted to use this again because if you don't know the third side, you have to find it. But we already did that. This third side was 1, right? We did that on our first example. So we do have the 3 sides of our triangle. All right, so we're going to find the sine of theta. You have to write the theta, right? It's the sine of that particular angle. And the sine of theta is the opposite over the hypotenuse. So what's the opposite side to theta? It's 1, and the hypotenuse is square root of 5, right? All right, we do not leave radicals in denominators. We don't do that. So there's going to be some caveats to that when you get to some calculus courses and so forth. But for what we're looking at here, we're always going to be seeing, I can't think of a single instance in trig, if there is one, I'll mention it later, where we have a square root of a number. We're going to be working with square roots of numbers. When you get to square roots of variables, it's a little different. When we have a square root of a number, we're not going to leave a square root in the denominator, we're going to rationalize it. And the way that we rationalize it is we multiply it by itself. So when we take the square root of 5 times the square root of 5, we get 5, right? So this denominator simply becomes a 5, and the numerator will stay the square root of 5. So are we going to still have a square root in the problem? Yes. We're just going to have it in the numerator instead of in the denominator. This is a convention of mathematics that's a little bit antiquated. I understand that, right? It's old-fashioned. It doesn't seem to be all that necessary, but it is still one that we use. So we're going to be consistent and use that. If we've already got sine, we should be able to get the reciprocal, which is cosecant, very easily. But don't do this in a hard way. We don't need the reciprocal of the square root 5 over 5. Like, it is not helpful for me. Don't write this. It is not helpful for me to rewrite this like this and then have to find the square root again on the denominator and simplify it. There's no reason to do that. Instead of doing that, let's come back to the location that was equivalent, which was at the beginning, where when I flip it, I automatically don't have a square root on bottom. Are you with me? It's fewer steps. Now, if you do what I just suggested before not to do, it's not the worst thing in the world. You're just going to have more steps involved. So if I flip this piece of it upside down, I'd have square root 5 over 1, or more simply, it would be just square root of 5. So this one is sine and it's reciprocal. Let's do cosine. It's a little friendlier. No, I'm sorry. I was thinking about tangent. We're not there yet. Tangent's friendlier. All right, so cosine would be the adjacent. What is the adjacent side? 2 over the same value for the hypotenuse, square root of 5. And we're going to do we're going to repeat the same thing in terms of multiplying by the square root of 5 on top and bottom. So we're going to have 2 square root of 5 over 5. And then for secant, which fraction is the most convenient to flip? The first one, right? The 2 over square root of 5. So let's flip that one. I have square root of 5 over 2, and I'm done. And then we're going to do tangent and cotangent. So tangent should be opposite over adjacent. Opposite is 1. Adjacent is 2. No radicals involved, so that's friendly. And then for cotangent, it would just be 2, or 2 over 1, which reduces to 2, or simplifies to 2. Okay? So these are our 6 trig values for this one. Now there's two triangles I'd like to mention. These are special case triangles, right triangles, and you've seen them again before. They come up in geometry, usually for the first time. And so the first one, we're going to put a right angle down there, is 1, 2, and square root of 3. It's a Pythagorean triple that's very nice. So I didn't write that in the right order. I'm sorry. 1, square root of 3, and then 2. That's the order I wanted. Apologize. This triangle is a very nice triangle. We're going to see it used repeatedly throughout trig. It's a 30, 60, 90 triangle. Okay? So its angle measures have exactly this measure. And when we see this, we're going to see this again when we work with a unit circle, which you may or may not be familiar with. We'll get there. But these are the side lengths that are opposite them. It's a memorization kind of thing. If we know this triangle, we can utilize it. Anytime you see a 30, 60, 90 triangle, you're able to find the side lengths if you only know one of them. You don't need to know all three, or even two, rather. You just need to know one of them. The other one is a 45, 45, 90 triangle. And its side lengths are 1, 1, square root of 2. So have that handy as you're seeing these different trig functions, and we're going to give an example here in a second, because if we just use the triangles that we already know, we don't have to recreate the wheel every single time. Right? It saves us time to have a little bit of things memorized. So as we take a look at these, this one says tangent of 30 degrees. Well, I'm going to jot down a reminder to us that tangent is opposite over adjacent. So if I come back to my 30 degrees is the one I'm looking at up here. What is opposite the 30 degrees in this triangle? Okay, not the angle, the side length. The 1, right? The side length that's opposite the 30 is the number 1, and the adjacent is square root of 3. So over here, opposite 1, adjacent square root of 3. And if we rationalize, we'll be multiplying by square root of 3. So I have square root of 3 over 3. Now, it's probably worth mentioning that if you put this in your calculator will not spit back out at you square root 3 over 3. It'll give you a decimal approximation. That's not necessarily a bad thing, but it's not going to give you the square root 3 over 3 value. You will not have the exact answer. You'll have an approximation. Pi over 4. Now, we worked with angles last time, where we worked with converting between radians and degrees. At some point, and it may not be today, pi over 4, you're going to immediately know exactly what angle that is. It's a 45-degree angle, okay? But if you don't know that yet, it means that you're going to keep working with these a little bit longer until that some of them start sounding familiar. And you're going to multiply this by 180 over pi. Okay? So 180 over pi is going to cancel my pi's. And then 180 divided by 4 is going to give me the 45 that I mentioned before. So that's one option. I'll show you another option for doing this. So I can rethink of this as the sine of 45 degrees, which is often how we have thought about degrees up till now anyway. So if I come back over here, one more thing. So this is opposite over hypotenuse for sine, right? So 45-degree angle, you can reference either of the 45s you wish. I'll use the bottom one this time. What is the side opposite 45 degrees? 1. And what is the hypotenuse? Square root of 2. So this one is 1 over square root of 2. And if we rationalize, we're going to get square root of 2 over 2. Okay? All right, one more thing, if you would like, you can go back to your triangles just a moment ago, and I'll write in the degrees. We wrote in the degrees, so let's write in the radians as well as a reference. So if that way you don't want to have to keep going back and forth, turning everything into degrees all the time, you can look at them in terms of radians. So we already mentioned that the 45-degree angles are pi over 4s, right? So let's change colors. Let's try yellow. So these are pi over 4. And in our 30, 60, 90 triangle, this one is the 30 degrees is pi over 6, and the 60 degrees is pi over 3. Okay? So if those come up and you want to think about the triangle in terms of radians instead of in terms of degrees, that's fine. At 90-degree angles, let me just mention real quick, that's pi halves. We've already seen that happen, but just as a reminder. Okay, everybody good so far? All right. We're going to be working later in the course with a lot of things that are called identities, and we're going to see them coming into play a little bit as we go. So an identity is simply an equation that holds true for any value of the variable in the function's domain. Okay, it's always true. That's an identity. So you've seen some of these before. You probably aren't aware or think of them being called this, but in an algebra course along the way, there was somewhere when you use systems of equations where you had to decide, does it have one solution or does it have infinitely many solutions, right? Or maybe no solutions, that's another option. The infinitely many solutions creates identities. That's where those are created, is where things they have infinitely many solutions. Reciprocals, which I already mentioned this, is the multiplicative inverse of a fraction. It's the flip, right? So if I take A over B, it's B over A. We call A over B and B over A reciprocals of one another. So that's just terminology to remind you. But these are the reciprocal identities. So I had mentioned when we looked at the triangle that when we looked at sine and we flipped it upside down, we got cosecant, right? And the reason that's happening is because sine and cosecant are reciprocals. So these are identities. No matter what angle for theta I use on the left and the right, because it'd be the same angle, I'm going to get the same value. So if you were to play with your calculator and to try this, it would be very nice. The trick is, though, that most calculators do not have secant, cosecant, and cotangent. They don't have them in there. And the reason they don't have them in there is because you can do reciprocal with any of the other three and get them. There's no need. So if I wanted to find, let's just do something real quick so you can see it. If I wanted to find the cosecant of 45 degrees, I wouldn't write cosecant of 45 degrees. My calculator doesn't have a cosecant button. I would literally put it into my button as 1 over the sine of 45 degrees instead. Okay, that's what I would do. That's how your calculator allows you to put those in. It is really important for you to realize that this little -1 exponent, which is used differently in algebra, not differently, but we'll talk about it later. It has a different meaning. This sign with the little -1 is not the same thing as 1 over sine. And I mention that because what you have seen before probably is that x to the -1 is 1 over x, right? Okay, that's not what's happening here. This has a different meaning, and it corresponds to this, but it doesn't look like it's fractions, okay? So you can't just go and say, oh, look, there's this little button that says sine -1. I'll use that one instead of doing 1 over in my calculator. It won't work. It won't work at all. Okay, we'll get to what that's meaning later. The next set of identities we have are called quotient identities. Quotient identities talk about dividing things. Quotient means division. So the tangent of theta is equal to sine over cosine. Now, I'd like to show you that that makes sense based on our descriptions where we described opposites, adjacents, and hypotenuses and all that stuff. We said that sine of theta is opposite over hypotenuse, right? And we said that the cosine of theta is adjacent over hypotenuse. Everybody good so far? Now, if I divided these, I could actually multiply by the reciprocal, opposite over hypotenuse, times, instead of adjacent over hypotenuse, it will be hypotenuse over adjacent. And look what's going to happen. Hypotenuses cancel, right? Because they're on the same, they're across diagonals of one another. And I would get opposite over adjacent, which is exactly what I called tangent. Okay, so all of these things play together very nicely. They have to, or they wouldn't be identities. And I could do the same thing to establish the cotangent if I wanted to. But these are not just coming out of nowhere. They're not independent of the others. They're interrelated with the others. So the tangent is sine over cosine, and cotangent is cosine over sine. Pythagorean identities. When we talked about Pythagorean theorem before, a squared plus b squared equals c squared. These are Pythagorean identities. And you'll notice that they're sort of appropriately named because we have squared pieces, right? So the first one is the one people tend to remember, sine squared plus cosine squared equals 1. I remember going into the ACT before I had taken trig, and I remember a teacher telling me, you should at least remember this about trig, even though you've never taken it. Sine squared plus cosine squared is equal to 1. It'll probably show up on the ACT. I don't know why I have that memory, but I do. Like, it's one of those things that people remember. Sine squared plus cosine squared is equal to 1. The other two are not quite as nice because they have the squareds on both sides. Tangent squared plus 1 is equal to secant squared. And cotangent squared plus 1 is equal to cosecant squared. Now, there will come a day later on where you're going to have a test over all the identities specifically. It's nowhere near right now. You got a long time of working with these before we're going to have them memorized. But eventually, you're going to have these memorized. And if you're sitting here and you're thinking, well, I don't really need to know that and all, whatever, we use them a lot in Calc 1 and Calc 2 and Calc 3. Like, they just keep coming back up. And every time they do, my kids are like, oh, trig identities again. Yes, trig identities again. So you're going to get to see these over and over and over again. All right, so we're going to use some trig identities to find some functions. So they're giving us a couple functions here. They tell us the sine of theta is 6 over 7, and the cosine of theta is square root 13 over 7. And we're going to use different identities, right? We've got 3 sets of them now. We've got reciprocal, quotient, and Pythagorean. We're going to use those 3 types of identities to find the 4 that are missing. We've got 2 of them. We're missing 4. Now, the 2 that are easy are the reciprocal ones. So what's the reciprocal of sine? Which of those functions is the reciprocal of sine? Cosecant, yes, indeed. So cosecant is one of the easier ones to find. Because what is the cosecant going to do with the sine values? Just flip them. And this one's really nice because it's not even got any radicals involved, right? The cosine's reciprocal, what's that? That one is secant. Now this one's a bit messier. When I flip this one, I get 7 over square root 13. And I do need to rationalize. So I have 7 square root 13 over 13. Okay, so even if you can't get all 4, those 2 are the easy ones to get. You should get those. Okay, that shouldn't be a big thing to do because those are the flipped ones. Now, tangent and cotangent require a little bit more work. I can't just flip something upside down. What do you think I might need to do in order to get tangent? We're going to divide 2. Which ones are we going to need to divide? Sine and cosine. So this is sine of theta over cosine of theta. So sine of theta is 7 over 6. Cosine of theta is 7 over, no, is that right? Yeah, 7 over square root 13. I didn't say it right. Square root 13 over 7. Go back up far enough. Okay, did I get them in there okay? All right, so we have fraction over fraction. We're going to flip and multiply. So 7 over 6 is going to stay the same. Top one always stays the same. The bottom one flips. It's
6 over 7.
Oh, this is what happened. I went up and I went to the wrong spot. I'm sorry. Thank you for fixing that. 6 over 7. So I'm going to show you my screen. Do you see how zoomed in I am? This is why I will lose things. So please tell me when I've lost things because I zoom in so that I can write really clear for you to see. But sometimes I lose pieces on my screen when I do it, okay? Thank you so much for that. Okay, so 6 over 7. And then I have the flip would be 7 over square root 13. Do I have that all written out right? Are we good? Okay, wonderful, because now the 7s are going to do what? They're going to cancel, yeah. And we tend to see a lot of cancellations happen when we work with these. So now I have 6 over square root 13. So I need to multiply by the square root of 13, yeah? So I'm going to get 6 square root 13 over 13. The last trig function is cotangent. What am I going to need to do for cotangent? Well, yeah, I can do 1 over tangent, a reciprocal identity. I could do cosine over sine, right? That would be another option. But I think that you're right, Isaiah. I think the easier way to do it is for us to actually look at one of these versions somewhere in here and flip them. And probably the one I like is this one right here before I multiplied by the square root of 13, excuse me. Because if I flip that, right, so let me box that one in. If I flip this piece upside down, I automatically won't have the radical on the bottom, right? So all of these things are equal, which means I can flip any one of them that's equal and make that work. So we're going to take the square root of 13 and it will be divided by 6. Now, if you forget to do that in the middle of whatever, and you take this, and then you flip it, and then you rationalize, you're going to get the same thing. Yes, ma'am?
When you say flip either one of them, are you talking about either one of the fractions or either one of the, like, cosine?
I'm talking about any of these fractions that we have worked with. So, like, I could flip this one, or I could flip the one that I marked, or I could flip this. Any 3 of these are all equal, so flipping any of them will end up giving me the same answer. Some of them just require more work than others. Thank you for that clarification. Okay, any questions on that? All right, so the identity that we didn't need to use in any of that was the Pythagorean one, right? Now take a note on this one. We are asked to find cosine. That's fine. I'm only given one trig function. I could be given this one trig function and asked to find all 6. I'm not, but it could be. Okay, if I'm asked to find all 6 of something, well, 5 that remain, and I'm only given one, right, then I'm going to end up having to use some kind of Pythagorean identity to do that. So the Pythagorean identity is the one that relates sine and cosine together. It says the sine squared of theta plus the cosine squared of theta is equal to 1. Now, the notation puts the squared on sine, right? The entire function is squared. So it's another way of writing it like this. It just requires parentheses. That's what it means. So they shift the 2 to be beside the sign to avoid people leaving the parentheses off and then realizing and thinking, do I square the angle theta or do I square the function sine? Okay, so that's why the little 2 is beside the sign, is they want you to understand you're squaring all of it. So we're going to rewrite this just to remind ourselves of what we're squaring in this. So it looks like this. They gave us that the sine of theta is equal to 7 over 8. Theta is not 7 over 8. The sine of theta is. So we have to replace all of sine theta for that to make sense. Are you with me? 5 of you are going to stick this in for theta. I don't know which 5. Don't let it be you, okay? It's common. We think that's the variable, right? Theta is the variable. They give me a value. I'm just going to put it in the variable. That's not what they gave you. They gave the sine value, so we need to replace the entire thing of sine. And then we're going to have the cosine of theta squared. All right, what is 7 over 8 squared? 40. Close. 49 over 64. Yeah, 49 over 64. And we're going to then subtract that to the other side, right? So we'll subtract 49 over 64. So if we're wanting to get common denominators, this would be 64 over 64. So what happens when I subtract 64 minus 49? Thank you. It's just 15, right? 64 minus 59. Was that had 49? Excuse me. It's 15, right? And then I'm supposed to be finding cosine, and this says cosine squared. So then I would square root. Yeah, I'm going to square root both sides, and just for clarity, I'm going to go ahead and square root both pieces of the top and the bottom separately. So cosine of theta. 15 doesn't reduce in terms of a radical because it's just 3 and 5. But the square root of 64, of course, does. What's the square root of 64? 8. So the cosine of theta is square root 15 over 8. Now, this is all we're asked to do here. But notice, I now have sine and cosine just like I did in the last problem. Could I find the other 4? Of course I could. Of course I could. And you might be asked to. All right, we're going to use an identity to find this value. Well, how are cosine and secant related? They're reciprocals. Yeah, multiplicative inverses are reciprocals, right? So I can rewrite secant how? It is 1 over the cosine of 53 degrees. So if I have cosine of 53 degrees multiplied by 1 over the cosine of 53 degrees, what does that give me? 1. It's just 1. right? They're reciprocals of each other. So I just get 1. So you're going to see some with values like this, questions like this as well. Complementary angles. Complementary angles, you see those in geometry as well. These are 2 acute angles whose sum is 90, right? That's why the 30 and the 60 were complementary, right? 30 and 60 added to 90, 45 and 45 added to 90, but you can do this with any values, right? So if I give you a number that's less than 90, we can find its complement. And because of complementary angles, we have another set of identities called cofunction identities. The cofunction identities talk about the fact that if you were to look at these graphs, all they really do is shift. Okay? So the sine of theta is cosine of theta of 90 minus theta, and the cosine of theta is sine of 90 minus theta. They're just shifts of each other. The secant of theta is the cosecant of 90 minus theta, and the cosecant of theta is secant of theta, which is of 90 minus 1, of theta, 90 minus theta. And for tangent theta, it's equal to cotangent of 90 minus theta. And then the cotangent of theta is tangent of 90 minus theta. There's a pattern here, right? It's a pattern. So when you look at this and you think, oh my word, there's 6 different ones to memorize and they all look messy. They're all the same, right? Now, you pair up the right pieces, but that's why they're called co-functions. Sine and cosine, secant and cosecant, tangent and cotangent. It's the co's that go together when we're looking at cofunction identities. But they're really all the same, at least all the same pattern. Okay, so this problem does not ask us to find the tangent of pi over 7. What it does ask us to find is a cofunction with the same value. So I want to turn tangent into its cofunction. So what is the cofunction of tangent? Cotangent, right? And what we had just written down before is that what do I have to do when this is the cotangent? Well, I have to subtract the angle, pi over 7, from 90. But how is 90 written if we're in radians? Because this was given in radians. It's pi over 2. So every single one of these, I didn't want to write them all twice, have the same thing here if I write pi over 2, right? Those are equal values. So since I'm working with the radians, I was given pi over 7, I want to use pi over 2. All right? And so then you're going to find a common denominator. So the common denominator would be 14. So I have 7 pi minus 2 pi over 14. And 7 pi minus 2 pi would be 5 pi. So I have 5 pi over 14. So the cofunction with the same value is cotangent of 5 pi over 14. All right, so what are these different identities used for? Well, they're used for a lot of things. So I'm going to do a few examples here. The first couple of them don't have any context really with them. The last one does. So we're going to find the measure of the missing labeled side. So it's not labeled because I didn't label it, I guess, but it's this side down here. It's the missing side. Should have said missing side. So we're going to find this piece right here. There's a couple of ways to do that, right? So we could use a Pythagorean theorem, right? That would be an option. You could also use use sines, cosines, tangents. So because we've already looked at one with the Pythagorean theorem here, I'm going to look at it from a different perspective just so you can see another way of doing this particular problem. And sometimes it's the only way. If I'd only be given one of those side lengths instead of 2 of the 3, this would be my only option. So let's use the 4 and the A and the 12. Let's say we did not know square root of 5, okay? So if I use these pieces of information, what trig function will relate the 12-degree angle to these two sides of my triangles? Think SOHCAHTOA. Tangent. It's tangent with the ones I've listed, okay? Tangent is opposite over adjacent. Okay, if you use the square root of 5, you could use cosine, because that would be the opposite of the hypotenuse you'd be using. So if I set this up, the tangent of theta is the opposite, which is a, over the adjacent, which is 4. And I should have written it in. I'll write it in now. My theta is 12 degrees. So what would I do to get a alone? I'd multiply by 4, right? And at this point, what you're going to do, 12 is not 30, 60, or 45. Those are the only ones that we know exact values for, agreed? So special triangles for those, that's it. What that means is at this point, your calculator comes into play and you grab it. And you type in 4 tangent 12 degrees. Make sure that you're in degrees, because this problem's in degrees. So make sure your mode is set up correctly. What do you get for that one? Did anybody type it in? 4 tangent 12 degrees.
0.85.
What is it? 0.85. Mine looks larger than that, but I might have had mine set up wrong too. What did you get? Let me look real quick. You got 0.85? Are we in degrees? Okay, I might have been in radians when I put down mine. Yep, you're right. And the directions say to round to the nearest what? Hundredths, and hundredth means 2 decimals. So 0.85 is where we would leave this. Very good. All right, we can also find missing angles. So in order to do that, we need to use inverse functions. So I told you that the sine -1 doesn't mean 1 over sine. What it does mean is this. The inverse sign is used to find an angle measure when we know the sine value, cosine, tangent, whichever one it is, of that angle. For example, if y is equal to sine of x, then the inverse sine of y is equal to x. So when we take inverse functions, we find angles. When we take functions, for right now what we're talking about, we're finding side lengths. Inverse functions find angles. And the easiest way to show this is to do an example so you can see what I mean, because it sounds kind of like I'm just playing with words a little bit. At least I feel like it does. And so if we do an example, it'll make sense. We're looking for theta in this question, and we've got 2 pieces given. Now, if I'm going to use the theta, right there, where it is, and I'm going to use the 2 and the square root of 5, what trig function is going to relate the 2 and the square root of 5 together? It is cosine. So the cosine of the theta is 2 over square root of 5. But somehow I've got to get theta by itself. And I can't divide by cosine because cosine is not a number, right? It's like you can't divide by square root. That doesn't make any sense, right? Nobody would even try to do that. We can't divide by cosine. It's not a number. So what we do is we do the inverse cosine. And we do it to both sides. And if you take the inverse cosine, that's the button in your calculator as well. You do inverse cosine of 2 over the square root of 5. You don't have to rationalize it or anything. It will give you a 27-degree value for that angle. It does say measure to the nearest degree on this one as opposed to 100th. Okay, real quick, give me 1 extra minute beyond class and we'll finish up the last one. This is a true application problem, like legit, right? It's got words and everything. We have a tower, it's 125 feet tall. It casts a shadow that's 172 feet long. So here's my tower. You can imagine it right here. Here's the tower, right? So the tower is 125, and the shadow is 172. And it wants to know what the angle of elevation is. So angle of elevation is always how we elevate our eyes to the horizon. Okay, so it's from ground level looking up. That's what angle of elevation always is. So it's talking about this angle right here. Okay? This is how sundials work, by the way. When you're trying to measure the time of the day is off the sundial, it works with these shadows. So you're lifting your eyes here. Here's my angle. What trig function relates 125 and 172? adjacent and opposite, which is tangent. Yep. The tangent does. And we're looking for the theta. The opposite is 125. The adjacent is 172. And then I'm going to do the inverse tangent, like I just done the last problem with inverse cosine, to find my angle. And it is rounded to the nearest degree. Your calculator does this step. If you're not sure how to make it do that, we can chat. It gives you 36 degrees.